Hello everyone, hope you all are doing great. I'm Dr. Nitu from University of Science and Technology, Meghalaya. The, as we know that this unexpected pandemic outbreak of a new disease COVID-19 has changed the way of life, but the situation has taught us a lot. This adverse situation teaches how to create a virtual classroom, virtual department, as in total, a virtual university as well. So, dear students, we already have come across the whole syllabus of this astrophysics part of GTR and astrophysics course, and today this is the last class I am going to deliver. So I called it the last lesson to the batch of 2020. Uh, you all know the story of last lesson. You probably read in your schools. So today we are going to discuss the Big Bang Nucleosynthesis, which deals with the light elements production, and we are also to discuss the chronology of the universe and the cosmological models of the universe. So let's start. Another thing, we can just uh, record a 15-minute video here, so it will be ended at 15 minutes, and the next part will be continued in the next video. Okay, so let's start with this. The first discussion here we are going to discuss our plan of discussion is the Big Bang Nucleosynthesis, which this deals with the production of the light elements. Here we will be discussing how the early elements, proton, neutron, etc., antineutrino, photon, etc., they produce the early elements of the universe, hydrogen and helium, lithium, etc., and their isotopes. So that will be under the Big Bang nucleosynthesis. Next, we will be discussing the chronology of the universe. Chronology will be starting from the very initial state of our universe, that is the singularity. Then that singularity has been exploded, and which is called the Big Bang, and the stage-wise development of the universe till today. We'll be discussing here. Then in the next topic, the cosmological model. Let's put this here. In the cosmological model, we'll be discussing three different type of models of this universe: flat, flat universe, open universe, and closed universe. We'll be discussing in detail in this topic. So let's start with this Big Bang nucleosynthesis. Before going to Big Bang nucleosynthesis, we must discuss about the Big Bang. This is mm, the Big Bang is considered as the early starting point of this universe. We, as we know that, let me get it. Yeah, uh, the universe initially was composed in a consisting, composed in a very tiny dot, which we are calling as the singularity. All mass were composed in that tiny dot. That was extremely dense, and the temperature was extremely high. At the temperature was around 10 to the power 32 Kelvin. That is very high temperature. So the Big Bang, from the singularity, the Big Bang explode, and all these elements has been created thereafter. After first it produce the elements, then the nucleus has been created, then the atoms, then the molecules, etc., etc. Then these are the stages, different stages after Big Bang of, and later on they combine together and form the galaxies, etc., etc. And today we are seeing those things in a different form. Okay, so I'm presenting here a video of, that is an animation made by CERN of Big Bang and its later development, uh, first few seconds development. Okay, let's start this video. Yeah, this is a sound footage. First see it, I'll be explaining it. I'll be running it again. Okay, this is this is here. uh, this is the singularity is explode. This is the Big Bang, and after the Big Bang, just after a few seconds, this particles, the elements have been the particles have been evolved. The early particles have been evolved. Then from those particles, the nuclei and later on the atoms, then molecules, etc., have been evolved. So this is the first few seconds of of our uh, Big Bang of our universe. Okay, I'm closing it. Okay, now we know that the Big Bang at the Big Bang, the temperature was very hot, so we call that the Big Bang. We say that Big Bang theory predicts that the early universe was extremely hot place, whose temperature can be goes up to 10 to the power 32 Kelvin. So uh, yes, this is the time as well as era scene of era, different era after the Big Bang. Just after the Big Bang, the era was Planck era. In this era, the time was 10 to the minus 43 seconds. Means if you divide this 1 second to 10 to the power 43 times, then one part of it is the Planck era. Very tiny uh, part of a second. In this Planck era, we have no idea what is there. Okay, because uh, how we'll be detecting? We'll be detecting those things by the light coming from that era. But in that era, there was no production of photons, so we don't have any idea about this Planck era. Neither the next era. Next era is up to 10 to the minus 35 second, and this is called GUT era, whose full form is Grand Unification Theory era. In this era, the whole all the forces were clubbed together, and we don't have any information of it. Then up to 10 to the minus 10 second, it is electroweak era. uh, Means the weak and electromagnetic forces were appearing at this moment, and up to 10 to the minus 3 second, the particles have been evolved. Then came the era of nucleosynthesis at around uh, 1 second after the Big Bang. Uh, Let me put myself somewhere here. Okay. Here you can see that after 1 second, the Big Bang, the temperature become 10 to the power 10 Kelvin. The temperature is reducing now, and the universe was filled with sea of neutrons, protons, electrons, and photons. Okay, as the universe gradually cooled, the neutrons either decay into protons and electrons, or they combine with protons to make the deuterium. So in this era, just after the 1 second after the Big Bang to 3 minutes after the Big Bang, so within that time time duration, these protons, neutrons, and the electrons, they have been evolved, and they produce the higher uh, heavier elements like deuteron, hydrogen, helium 3, helium 4, etc. We'll be discussing those things in the next slide. So the next slide deals with the Big Bang nucleosynthesis and the production of light elements. Here we are presenting the periodic table. Here we know that the light elements fall in the left side and heavier elements fall in the right side of this periodic table. Here hydrogen and helium are the first produced elements of this universe, so they are put first. So first, that elements were hydrogen that created from This neutrons, protons, neutrons, and neutrinos, etc. Their interaction, from their interaction, then the hydrogen converts to helium, and this conversion is given by here. Four hydrogen mix together to fuse together to give a helium and lot of energy. That was the conversion scheme from a element to a heavier element. So here we will be discussing how the light elements of the early universe have been evolved. The early elements were hydrogens, deuterium, helium-3, and helium-4, from where lithium also has been evolved. I have forgot to write it here. So in the next slide, we'll be discussing how they will be and from which reaction they will be evolving. Okay, so coming to the next slide, the reaction that produce the light elements just after the Big Bang. The first reaction we are putting here, this is the neutron-proton reaction. These uh, these reactions have been started just after 1 second of the after the Big Bang. So neutron and proton reaction occur to maintain the neutron-proton ratio in the thermal equilibrium. Here you can see the proton is combining with an electron to produce a neutron and a neutrino. Then that neutron will combine with another proton, another electron, and to produce a proton and an antineutrino. These two are reversible process, and this reaction maintain the ratio of neutron to proton, and this ratio was 1:6. The next reaction was the only reaction that abruptly changes the number of neutron is the neutron decay. So neutron decays to proton and electron and also an antineutrino. That again the proton and electron are evolved from a neutron. The reaction, the third one, the reaction to preserve the neutron occurs by the deuteron formation. Okay, neutron and proton then combine to give a deuteron and a photon, means a gamma ray. But here we need to say that the deuteron is the nucleus of deuterium, a heavy form of hydrogen 2. This reaction occurs when temperature of the universe reduces from 10 to the power 10 Kelvin to 10 to the power 9 Kelvin. The temperature of the universe is gradually decreasing with time, and the reaction processes are going on. The further reaction takes place to produce radioactive form of helium, helium-3, and the light helium, H3 and helium-3, and normal helium, helium-4. The reactions are deuterium combined with neutron gives a H3 and gives a and produce a photon. This H3 combines with a proton and gives the helium-4 and also a photon. Then deuterium combined with proton and gives a helium-3 and also produce a gamma ray, and helium with neutron produce a helium-4 and gives a photon. These are slow reactions. They proceed with the photon emission. I have only 1 minute to close up this session. Then next next reaction is few fast non-radiative reactions also takes place. These are the reaction process, and here you can see that deuterium combine to give helium-3, deuterium combine and a neutron. Here deuterium combine to give a hydrogen-3 and a proton. This hydrogen-3 plus deuterium gives a helium-4 plus neutron, and helium-3 plus deuterium produces a helium-4 plus a proton. So uh, what we have seen that early universe light elements, which are composed of hydrogen, deuterium, helium-3, helium-4, etc., they have been produced from these reactions. These reactions were only